Welcome to the second part of 4.1. We're going to go through and talk about population growth. I'm going to talk about how we can quantify that. So let's first talk about some terms. Natality is just another term for the birth rate. Now you might also see some other stuff that they say like per capita, and that usually just means for a certain amount of people. Usually it's 1,000. And so they're saying if we take a random 1,000 people from within this population, within a year, how many offspring will they have? And so this gives us a general measure for how many births there are, because that way we can compare populations that differ in size. I don't want to say, well, China has so many more births when they have so many more people. So that doesn't tell me on average, are they having more births per a certain amount of people? Like, are they actually having where 1,000 women would have more children in a year than 1,000 women in the US or in Nigeria? So per capita allows us to compare populations regardless of how big they are to get a sense of how often they're giving birth. And mortality will work the same way, except this is going to be the death rate. So they'll look at a set amount of people and say, on average in a given year, how many of them will die out of 1,000 people? Or in some cases, you'll even see them used per 100,000. So these are ways to compare populations, how many people are being born, how many are dying. Now that's part of how we can determine population growth. Part of the way we can do it is say how many people are we adding births, how many are we subtracting deaths. But there's other ways to get people in or out of a population. You can have individuals that have already been born can enter your population through immigration, so they come in. So this is like we have immigrants to the US that leave somewhere else to come here. They're not born here, but they are here. So they're still part of our total population. We can also have individuals leave the country, leave the population, and that would be when they exit, so emigration. So this is another idea of how we can lose people, not just to death, but also to them just leaving. And if we go through and do this calculation, we solve for something called the R value, the growth value. Now, if this number comes out positive, where the births and immigration exceed or are bigger than the deaths and the emigration, then that means the population is currently growing. The bigger the R value, the faster you're growing. Whereas if I get a negative value here, if this side of this equation is bigger than that one, then ultimately we're going to see that the population is shrinking. That population is going to be getting smaller and smaller. The bigger the negative R value, like the more negative it is, the faster it's shrinking. So with this, just to make sure we're clear, R value, rate of growth, can be getting bigger or smaller. K value, which we haven't discussed, is the carrying capacity. This is essentially the max population that a particular environment can support long term. So at some point you hit a limiting factor that says, yeah, if you have more people, they're just going to end up starving to death, or disease will run rampant, or something's going to limit their size. And then lastly, N, this capital N, just means the number of individuals. So I could say that N equals, 100 individuals in a squirrel population, and there's nothing wrong with that. That's just saying 100 squirrels. That's my N value. Now, when we look at growth, there's two patterns of growth that we're going to look at. The first one is a type of pattern you tend to see with organisms that tend to be in unstable environments, that tend to grow rapidly, and this is called exponential growth, where individuals grow faster and faster and faster. And so we get this J-shaped curve, where when you look at this graph, you can see it kind of resembles a J. And the reason for this is if you have a population that doubles at a set time interval, so let's say it doubles every year. We start out with 2 people, and after a year it doubles to make 4. And after a year it doubles to make 8. And then it doubles to make 16, then 32. And if you notice here, if it keeps doubling at the same pace, you first only added 2 people, then you added 4 people, then you added 8, then 16. So each time we go through a year, we add more people than the previous year. So our growth now is picked up. The increase that we have is even faster than it was. And so that's why you keep getting where it gets to a steeper and steeper slope here. It gets to a steeper and steeper line because we're adding more and more people each interval. That's exponential growth. This is what you see mathematically when you deal with exponential graphs. It's the same idea. So this will occur with many organisms when they first populate an area, or many organisms that live in an area that they don't live in long term. We'll explain that more later. Then logistic growth is when you take into account limiting factors. So this is an organism that's going to be around long enough that it's going to hit some limiting factor here that will slow and eventually stop its growth. So we see it starts off exponential, so this first part is still exponential, but it stops then growing exponential and it starts to slow. It doesn't stop immediately, but the growth rate slows until eventually r equals 0. The growth stops. We balance out. And we call that point where we balance out the amount that the environment can support. That's the carrying capacity. So carrying capacity is typically how many we can have and support total. Now, carrying capacity can fluctuate sometimes based upon the year. We normally try to use an average and use that as our long-term carrying capacity. But if you have a drought, your carrying capacity could drop for a bit. If you have a lot of rain that summer, it might go up a bit. But this is the max that can be supported before we start to see people hitting that limiting factor and starting to die out, not being able to sustain it. Now, you might see them referred to an S shape. That's just the way that this graph kind of looks like a stretched out S, where you start out with that J shape, but then you go in reverse and it kind of goes back to being flat. So it looks a little bit like a stretched out S. So if I say S shape, logistic. Now with reproductive patterns, these are the two kind of strategies that many organisms will take to try and survive. If you're a small organism, if you're an organism that's in an environment that oftentimes changes rapidly, so maybe like in Ohio, if you're an organism that can only live during the summer because you die if it gets cold. You know, if you're an organism like a fungus that grows on the bread that you have, but then after it eats all that bread, it might just starve to death because there's no more food. They tend to favor the rate strategy, the R strategy. And this is where you have a lot of offspring and you rapidly colonize. So you get lots of individuals quickly. Exponential growth, definitely. Rapid exponential growth. But because your environment tends to be unstable enough that you're not going to be there long term, you don't have like this long-term end game. You just populate as fast and furiously as possible. And many of these organisms will eventually crash and go extinct in that particular area. You know, the bread runs out, they die from lack of food. You know, you die out in the winter. But then when the conditions get right again, you go crazy while you can. You know, feast and famine, you go nuts. So this is the R-type strategy. This also works if you're an organism that tends to be fed upon a lot, where you might have lots of offspring because you know so many of them are going to die. You'll see some of them that have this kind of R rate mentality where, all right, I'm going to have as many kids as possible so some of them will make it. This does very well with small, short-lived individuals. But if you're looking at more of the long game, if you're larger, you have a longer life, so you know you're living 20 years, you're planning on staying in that habitat indefinitely, you're not playing any of these short games. You're trying to make it there as long as possible. And so these types of organisms tend to follow logistic growth, where initially they'll grow exponentially, although usually still a bit slower because they tend to have fewer offspring. You know, think like an elephant. You can still have elephants grow exponentially, but because they only give birth every few years instead of every 30 minutes for a bacteria, this can ultimately take them a lot longer to finish their exponential growth. And when they do, it's because they reach this limiting factor. So these guys will tend to hover around carrying capacity because they're there long enough to reach that plateau. They're there long enough to have the limiting factor limit their population size. And these guys do very well in stable environments. So environments where they're not going to have to kind of quick go and then crash. These are organisms living in places where they can survive normally year-round. And so they're not trying to plan just for the next week. They're once again trying to plan indefinitely. Now, with this idea of the R strategy and K strategy, we can look at survivorship curves. This oftentimes informs us of what strategy something's going to use and why. So if we look at something like elephants or humans, we notice that they are fairly strongly K-selected. They're K strategists. Now, the reason for that should be kind of apparent because they don't tend to die when they're young. They tend to die from things like old age or disease. These are guys that have long, stable lives for the most part. So this fits very well with that kind of K-selected idea. Now, when you look at type 3 survivorship, things like sea turtles, frogs, many insects, they very rarely reach adulthood. Once they do, their chances of living go up. So they can, if they can make it to adulthood, they do get some measure of safety. But in general, their chances of making it to adulthood are slim. So this one would fit very nicely with the R strategists, where we're going to have lots of offspring to try to overcome the fact that not many of us are going to make it to adulthood. It's like the cicadas will overwhelm our predators, if you will. So at least some of them make it. And if they do make it, if they do kind of win that lottery, then they'll probably be in much better shape and they can live long enough to have offspring, lots of offspring, so the population continues. And then in between, we've got type 2 guys. This would be like squirrels, songbirds, where they have about an equal chance of dying at any point in their life. If you're an egg, you might get eaten by a predator. If you're a chick, you might get eaten by a predator. As an adult, you still might get eaten by a predator. There's still plenty of things that go after you. So these guys have a fairly linear relationship, this kind of flat line here, because there is no one point where they're especially safe during their life. It's pretty much the same throughout. Now I want to notice too, just real quick, keep in mind there's lots of organisms that fall in between the R and K strategists. Don't assume everybody's got to be really K selected, where they tend to have these long lives, few offspring. You'll see some things like sea turtles do tend to have a fairly K-selected, long-term logistic growth pattern to them, even though they have more of a reproductive strategy of an R strategist. Lots of offspring, few of them make it to adulthood. So there will be plenty of guys that are on this spectrum, this gradient that has the really K-selected guys on one end, like elephants, and the really R-selected guys on the other end, like fungus or bacteria. But in between, don't assume it's got to be like one or the other. You're going to have individuals that can be mostly K-selected, like rabbits, where they do have this logistic growth pattern, but they still have quite a few offspring because they're trying to deal with predation. But they're not having quite a few offspring in the sense of when you look at many things like the tadpoles, where you can have hundreds or thousands of tadpoles to get one frog. We don't see rabbits churning out litters of 1,000 bunnies. So even though for us, we're like, they crank out a lot of kids. Once a month they can crank out, let's say 5, maybe 10 bunnies. That's a lot for us. But if you compare that to something else, like certain amphibians or snails, you might say, holy crap, that's nothing. Those snails can lay eggs once a week and they can lay clusters of 50 eggs. That's way beyond what a rabbit can do. So it's a spectrum. They don't have to be one or the other. And then lastly, we have age structures. This is how we try to diagram out a population to figure out what's going on. So we're going to take a population and break it into 3 groups and try to figure out how many people there are in each group. So when we do these groups, we're going to have the first group is the youngest group. This is the pre-reproductives. So these are the babies, the children. These are ones that are going to become reproductive soon, but right now they cannot have children. The second group will be our reproductives, people capable of having children. And then in many species, they can live beyond their reproductive years, like humans. You can still live post-menopause. You have the post-reproductives. So this would be individuals that are in older age. And so if we map this out, we can get a sense for what a population is doing. The more pyramid-shaped it is, and the more exponentially pyramid-shaped it is, where you get that J kind of curve to the pyramid, the faster you're growing. So if you have more and more and more babies, it looks like, each generation being born, and you've got a lot more early reproductives than post-reproductives, this is a population that is going to be going through rapid growth. This would be places like sub-Saharan Africa where they are growing very, very rapidly right now. When you start to get a more traditional pyramid look, where it gets to be a little bit less exponentially side-looking, where it gets to be a little bit more consistent, a little bit more linear, we still have growth, but it tends to be less rapid. You'll see that we're still getting more and more kids, but not as many more kids. It's not ever-increasing amounts of kids. With this one, you get where each time you add a new generation, you don't just add 10 more than the previous, you add 10 more, then 20 more, then 40 more. So we don't have that exponential idea when we have this traditional pyramid shape. So growing, but slower. As you start to get where it gets to have flatter sides, where you see it stops having as much of a pyramid shaped, it'll still diminish as they reach old age. But if it's fairly flat through the reproductives and the pre-reproductives, that's where we tend to see little to no growth. And so you might see this called zero population growth, where it's essentially staying the same. You're pretty much you're replacing the people that died, but that's about it. And then lastly, you can get where it tucks in, where you have fewer kids than you have reproductives. So we're actually getting where the younger generations are smaller than the older generations. And this is usually a very big sign of declining population. So if you've got a population like Japan, where they are having, on average, 1.3 children per couple, so 2 people are replacing themselves with less than 2 people, you're going to see the population decline because you're having more people dying than are born. That's the basic math. If you have more people die than were born, you're going to decline. So if we see some of these pyramids now, which we do in certain parts of the world with humans, we can see that this is going to be declining population size. So this is actually going to be a shrinking population. It's not just slowing its growth like these guys did over here, kind of 2 and 3 on our list. They're slowing growth, but they're not shrinking. This one is actually shrinking. So populations that are struggling because of pollutants and limiting factors, human influence, a lot of them are actually getting smaller and smaller. We're losing individuals. That's going to be what this model would look like for them. They would have this shrinking growth model.